Let's construct a diagram of the orbit and call it our position diagram. Let's divide the orbit up into 8 45-degree increments of azimuth. As we proceed, remember that I propose to index velocity vectors at a particular moment in time according to the angle of azimuth of the planet at that same moment in time. Therefore, another name for Vmax is V0. Over the course of each increment, gravity produces a vector, a delta V vector. Because delta V over delta theta is constant, the delta V vector for each 45-degree sector is of the same magnitude, and each points toward the sun. For simplicity, I will label each delta V vector according to the order in which they influence the motion of the planet. What do we get when we add Vmax and delta V1? Let's move them out of the position diagram and into a vector diagram and find out. In order to see what's going on more easily, I am going to scale up each vector by a factor of 3 when I put it into the vector diagram. Here we see the elegant simplicity of adding vectors. We put the tail of delta V1 at the head of Vmax, then construct the resultant, V45. We can continue the process by adding each successive delta V and constructing the corresponding resultant as follows. Now we can take our collection of velocity vectors and replace them into the position diagram along the orbital path, with each one being placed at the appropriate angle of azimuth. In this case, we can see a problem. Some of the velocity vectors are clearly not tangent to the orbital path. So either the ovoid is the wrong shape, or I have drawn it with the wrong dimensions. To find the right orbital path, we need to go through a process like this in a more quantitative way, and we will be ready to do so in just a moment. First, look at what we have left in the vector diagram. We can call it the delta V over delta theta envelope, which can easily be seen, in this case, to be a regular octagon. To help us remember that traveling around the vector envelope in the vector diagram corresponds to traveling around the orbital path in the position diagram, let's add in angle of azimuth designations around the envelope. Now we can see the versatility of the delta V over delta theta envelope. For example, let's erase all velocity vectors except for Vmax. Then let's take Vmax, scale it up, and put it into the delta V delta theta envelope. Let's say we want to find V135, the velocity at 135 degrees of azimuth of the planet. We don't even need to draw in the intervening resultant velocity vectors. We simply add Vmax plus delta V1 plus delta V2 plus delta V3 and draw the resultant. Now, what if we had divided up the orbit into 18 20-degree sectors? Then our delta V, delta theta envelope would be an 18-sided polygon. I think you can now see where we are going with this. If we return to the realm of infinitesimals and divide the orbit into a number of sectors approaching infinity, we would wind up with a vector envelope such that it would effectively be a regular polygon with an infinite number of sides. Namely, a circle, the dv d theta circle. The dv d theta circle gives us maximum precision and versatility as a tool. If Vmax is known, you can immediately find the velocity vector with the correct orientation and magnitude corresponding to any angle of azimuth. For example, I can immediately find Vmin and move it into the position diagram. At this point, given a planet's position and velocity at perihelion, we can find a planet's velocity vector corresponding to any angle of azimuth. What we lack is knowledge of the planet's distance from the Sun at each angle of azimuth. For example, does the Vmin vector go where I just placed it, or does it go here? Or here? This is where we go beyond Feynman's lost lecture and use his dv d theta circle to give us that additional information.